Hey guys, we're looking today at worded related rates. So we're taking what we learnt last lesson where we revised some related rates just using the chain rule, and now we're adding some worded problems. So it definitely steps up a notch here. So the first thing I've said here in the pink box, probably the most important thing to know for today, that the rate of something means the derivative of it. Okay, the rate that something is changing is the first derivative. So a lot of these are application questions, so we're involving real life examples. So we look at a lot of volume, area, or length. Now, the area there can also represent surface area. Okay, so a lot of the time they'll represent surface area with A, just shortening it for area. So if we want the rate that volume would be changing, we would do the derivative of the volume. So the derivative of the volume with respect to time. Okay, so these are all with respect to time. So if we want the rate that the area or the surface area is changing, we would do the derivative of that equation with respect to time, and same thing with length. Now, before we move on, just some formulas to remember. Sphere, these are just two formulas that you just have to remember off by heart. The cube, well, hopefully that is obvious to you, especially the volume one. It's r cubed because we would just do base times height times by the depth, which would just be r, representing, for some reason, they've stuck with r, even though it's not the radius of a cube, but the side length being r here. So it'd be r times r times r to find the volume of that, which would give you r cubed. So then for surface area, you would do, surface area is just the area of the front, the area of every side added together. So the area of the front shape would be r times r, because it's base times height, which would give you r squared. And then that's just the area of one of the squares. And then, of course, being a cube, there's 6 of them. So that gives you the 6r squared. But anyway, let's have a look at an example of how this can all come together now. So pause the video and copy this example down for me, and we'll go through it. So we've got an ice cube. So first thing I'm thinking about, okay, I got a cube. And it's melting so that an edge length is decreasing at a rate of 0.5 millimeters per second. At what rate is the surface area decreasing when the edge is of length 400 millimeters? Okay, well, let's think about what have they given me. They gave me some information here. They said that the edge length is decreasing at a rate of 0.5. So if I just stick with the weird lettering they chose to use before and represent r being the edge length, what they've just told me is that the derivative, the rate that that's changing with respect to time, is 0.5. Okay, so they've said, and that's their wording there, a rate, that's the key word. Okay, so that's just a piece of information they give me. What do we actually need to find? It says at what rate is the surface area decreasing when the edge length is 400? So what they want us to find is, if I represent A being the surface area, they want us to find that, ultimately, and then substitute in 400 to my answer. So I think, okay, let's think about what we learned last lesson. If I need to find that, let's look at what I already have a piece of information of. I already know dr dt. If I put that in here, let's think about now what fraction I would need to multiply by using the chain rule that would give me dA dt. Well, have a look at this. If I multiply by dA on dr, I will get dA dt. Because, look what happens. My dr cancels with my dr, and then I'm left with dA dt. So it was just a matter of me, I worked those exact figures, letters there out myself to know that I need to get dA dt as the final answer. So, what do I know? Okay, well, I know that dr dt is 0.5. dA dr, I don't know that. But all that's saying is the derivative of the surface area with respect to r. You think, okay, well, hang on. I know the surface area with respect to r has this formula. SA equals 6r squared. So if I start with that, and I'll stick with just A, because that's what I've already used, 6r squared. Well, then dA with respect to r, because I'm differentiating with respect to r, if I differentiate this, I get 12r. So now I can pop this in here. So therefore, the derivative, or the rate that the surface area is changing, is 6r. Now, they want at what rate is it decreasing when the length is 400. So therefore, when r equals 400, dA dt equals 6 timesing by 400, which gives me 2400, and it's millimeters per second. And there's my answer. Okay, let's have a look at another one. Okay, EG2, copy this one down for me. I'll just zoom in a bit. And then pause the video while you're copying it down, because I'm going to jump straight into it. All right, we've got a spherical balloon. So straight away I'm thinking, okay, I've got a sphere. All right, it's being inflated, so it's increasing. Its radius is increasing at a rate of 2 centimeters every minute. At what rate is the volume increasing? So what we need to know is, the question wants dV dt. That's what we need to find out. And then sub in 7 centimeters. What do we know? Well, what did they just tell me? They told me that the radius is increasing. So I know that dr dt is equal to 2. All right, putting that into my formula, dr on dt, what do I have to multiply by? Well, here I need a dv, and I need to get rid of dr. So I need to find what the derivative of the volume is with respect to the radius. Well, that's easy. I know that the volume of a sphere is 4/3 pi r cubed. So if I differentiate the volume with respect to the radius, so with respect to r, I'm going to have 3 timesing by 4/3 pi r squared. Cleaning that up, it's just going to cancel my 3's nicely, and I get 4 pi r squared. Okay, let's sub it all in. So I get dV on dt is equal to 2 timesing by 4 pi r squared, which simplifies to dV on dt equals 8 pi r squared. So that's the rate that the volume's changing with respect to time, and we don't want at just any time, we want when it's 7 centimeters. So subbing that in. So you should, I've just left it in terms of pi, 392. And this is centimeters per minute, because that's what the question gave it to us in. All right, let's do one more. Okay, here's a final question. So we've got this time, it's slightly different, but it's going to be completed in the exact same way. A particle moving, and its velocity is given by that where x is the displacement. If the rate of change in displacement is a constant of 4.2 centimeters per second, find the rate of change in velocity when the displacement is negative 4.7 centimeters. So, a lot to take in there. All right, let's start with what do they want us to find? The rate of change in velocity we want at the end of the day, which is dV on dt. So ultimately, that's what we want. What have they given me? They gave me that the rate of change in the displacement. So they said x is displacement, so I'm going to use x, not a d. So the rate of change in displacement is 4.2. So put that in as what I know. And what do I have to times by? Well, I must need to times by dv, and I need to get rid of that dx. So now, what do I need to find? I need to find dv with respect to x. So, well, good news. They gave me my velocity in the question with respect to x. And I know that to differentiate velocity, I actually know velocity differentiated is acceleration, but that's besides the point of this question. If I differentiate that with respect to x, I get 24x squared minus 10x minus 3. So now let's sub it all in. It's not very pretty, But I would just leave it like that and then be just very careful in your calculator, because we need to then sub in when x is equal to negative 4.7. Then putting all that in very carefully in your calculator, you should get an answer of dv dt equals 2411.5 centimeters per second. Okay, so I actually took that example straight out of your textbook, so I won't include that as one of the questions to do, but I'd like you now to have a go at the rest of exercise 811, but not every question that you haven't done yet. So I'd like you to do the following. So 9 to 13 and then 18 to 23, please.